All right. Hi, I'm Garrett. I'm presenting a joint work with George Wang, Jesse Hoogland, Dan Murfitt, and myself on interpreting small language models with susceptibilities. Well, uh, so you may have seen a paper we submitted about a month ago. Um, in particular, you may remember at the end of the paper, we speculated we may be able to do structural inference by putting a bunch of stuff into a big matrix and uh, taking the SPD of that or some other matrix decomposition, but we didn't do that. Um, we tried doing that and then it worked. So if you read the previous paper and you're like, oh, I don't need to care about this presentation because I read the previous paper, then fear not, you will be bored for only most of the presentation. Anyway, so the content here it is. First, I'll be reviewing the main equations that will be used here. These are going to be things that we talk about later. You're not expected to understand them right when I show them, but keep them in mind as we're learning. Um, the notation, that's just the boring stuff that you see in the beginning of all these talks, defining the posterior and the data sets and stuff that we'll be using. This time it's a little bit different because we're dealing with perturbations for each of those different quantities. So like you'll just see some subscripts there. Uh, but it's basic. It'll look like a giant screen with a bunch of nonsense on it, but it's just what you always see all the time. Then we're going to get to the setup, where really that's just motivation for why should you care about this, and then what susceptibilities actually are. Um, there's a thing instead of the susceptibilities called the observable. You'll figure out what that is, but that's in 5. That's when we'll know what that is actually, what we're using in the experiments. Um, and then what do the susceptibilities mean? It's not clear just staring at the function, or like it's not obvious just staring at the function. We'll cover that. And then we'll go and do some actual structural inference, and we'll get to the actual empirical results that we get when we do this on a small language model. So the equations. We have the actual susceptibility equation, um, and we have a more computationally tractable form of the susceptibility, which ends up just being a covariance up to order 1 over n. Uh, we can use that covariance form to define a per token susceptibility, which ends up being useful in structural inference. Very useful for structural inference because you can actually correspond parts of the model to parts of the data because we have those are particular samples that we could find a susceptibility with respect to. And then the observable that I talked to before, that phi, you could see the phi. I don't know if you could see can you see my uh, thing?
Yep.
Great.
So, yes.
Um, and then, yeah, the observable, it's the phi that you see in all these other equations. So first, the equation or the notation, as I said, looks like a bunch of nonsense, but you know this. We have our model, P of y given x and w. Y is like it's a token, it's the output. X is the input that you give your model, w are the weights. Um, we have the true generating function, q of x and y, and then it's a conditional form. We have our prior, I of w. Data set drawn IID from Q, our negative log likelihood function, and then the average negative log likelihood function, uh, negative 1 over n sum of the log probabilities, and the average, the negative expectation of the log probabilities. And then the quenched posterior, which is just the W is updated on uh, an expectation that W is updated on uh, the data. So we use the L here instead of ln, and then normalizing uh, constant there. And then this is exactly the same stuff, except we have a bunch of h's everywhere, and those represent the fact that we are perturbing the generating function here. So QH, X, and Y, what does that mean? Well, for most of this, it just ends up meaning we have the normal posterior, or the normal generating function, like the pile. That's what we trained our model on. And then we slightly increase the amount of, say, GitHub or archive in the pile. And then we increase it by like H. Like instead of having a normal baseline probability of getting the pile, you like increase that probability by H. And then that's QH, X, and Y. And then that has repercussions. D changes because now you're sampling from QH, so we write DH. L changes because now you have your X's and Y's coming from H. We write XI prime and YI prime. Your expected average negative log likelihood function changes to have the QH down here and the H up here. And our quenched posterior is now also a function of H, just because the L influences it as well. So now we get to the setup. So a fundamental thing that we want to understand is how the structure in the data influences the structure in the model. On the left, we have the various data generating functions, Q prime in D, like GitHub or Archive or DeepMind's mathematics dataset, which are sent to a quenched and tempered posterior by our F here. Now this posterior, it's living in an infinite dimensional space, so it's difficult to actually measure. So we have to choose a finite number of observables we can measure. Those are the phi sub j's. These are functions from W or prob W. Well, the phi's are functions from W to R. We take their expectations so that they are functions from the posterior to R. And then we wrap each of those expectations into a vector valued function G. So we're going from different true distributions of our data that our data is sampled from to a posterior for each of those distributions. And that's a quenched posterior that's using the average L rather than the Ln. We're going from different true distributions our data is sampling from to a posterior for each of those distributions, and then to a set of observables that are expectations over that posterior. We can compose those, so we just go from the data distribution directly to the vector. So that's G of F data distribution to our vector. And this is all we do to get to the susceptibilities, because after that, we just take the Jacobian of this. This is a function from perturbations in our data, which are parameterized by H, to a vector valued finite dimensional function, and we just take its derivative. Yeah, so we turn this into a linear algebra problem. For each of our observables, we can find the derivative of that observable with respect to small changes in the data distribution. For example, if our center point over here is the pile, we would ask how these expectations over observables change if you slightly increase the proportion of samples from archive or DMF. And so that's what we do. This is the expectation. And we're finding the derivative of the expectation with respect to H. And we have a 1 over n beta for reasons we don't have to get into immediately. So this is kind of hard to compute because we need to take this expectation, this derivative of an expectation with respect to all the different posteriors that not posteriors, but well, perturbations on the posterior, different perturbations on the data set that we want to do. Luckily, as I said before, we could approximate it using a covariance form with respect to our unperturbed posterior. So we go from a theta, or a phi here, whose expectation with respect to h, and we just find the covariance of phi and delta L, where delta L is a derivative of delta L is a derivative of the log loss with respect to h. That is not as horrible to compute because we don't have to rerun samples. Here we're doing expectations. Here we're just evaluating the loss on a sample from each of the different data distributions. That's easy. And this is the QH I was talking about before. We have 1 minus h times our original distribution plus h times our what we call our probe distribution. So this is our pre-training distribution, this Q, and we call the Q prime our probe distribution. That gives us our QH. So first question of the night, who wants to go through the proof? Or who wants to not go through the proof?
I vote to subject everybody to the proof.
Does anyone want to put Dan?
I vote
But
to
I
be
think
subject.
my vote doesn't count.
Oh, nobody is debating you.
Maybe we all want to see the proof.
Yeah, that's
Great.
right.
Yeah.
Okay. So this is the first part of the proof. It's just a bunch of it's very basic and simple. So we have our n beta chi, so we're just getting the chi into a just derivative of expectation form. Then we expand out the expectation here. Here's our phi, here's our expanded out posterior. And then we basically do a chain rule, or not a product rule, and then a chain rule. So product rule, we split off derivative of 1 over Zn beta h. That gets us this component, and we'll show why in the over here. And then, yeah, that gets us this component over here. And then we have the 1 over Zn beta h, and then we take the derivative of QH of W. Yeah, QH of W. And the derivative just goes inside of the integral, and we don't have to do anything else because this is the
You said
first part.
QH a couple of times when you meant phi, I think.
Yes, I did. Phi h. I mean, they look similar. You got the derivative of phi h that goes inside of the integral, and so it goes inside of the expectation here. And then the 1 over Zn beta h goes away because it just gets eaten up by the expectation. And then we take the derivative of this LH of W that pops out, or the minus n beta pops out, and so does the derivative of LH of W with respect to H, because it's how derivatives work. And the expectation stays the same, or, well, yeah, the expectation stays the same, but the x function stays the same. And so we have the QH of W phi times the derivative of LH, which is delta L. And we evaluate that at h equals 0, which just ends up being phi. We don't write the 0 because that's sad to write the zeros all the time. Yeah, so let's go and discuss why the derivative of 1 over Zn beta h becomes this thing. So it's just we basically end up taking the derivative of this x thing, and then that all the inside goes out, and we take the derivative of LH of W, and then the minus n betas come out, and so does, and the minus n betas come out, and we end up with a, what's it called? Yeah, the minus n betas come out, and then the expectation eats one of the zn beta h squares, and then we have the n beta over zn beta times the expectation of delta L. At h is 0, that's why we don't write the h's there. And then we combine, well, I guess we combine 2 and 5. And we get the final answer. Wait, no, we don't combine. We do combine 3 and 5 because we have this thing here. We're taking the derivative of that, and that ends up, yep, canceling out with u. That makes sense to everyone. I'm sorry if it didn't. I could go through things more detailed. I didn't expect that to make too much sense. It's not too detailed, but I hope you got the gist.
I expect everyone was following.
Cool. So if the data perturbation we're using is like the example I gave before, that is increasing the proportion of data sampled from archive compared to the pile or GitHub compared to the pile. Oh, my notes are out of sync. All right, we got the covariance form of the susceptibility, and we're on to the per sample or token form of the susceptibility, which we define as the covariance between phi and a particular, and our log loss on a particular sample. So we choose a sample, we find the log loss on a particular sample, and we subtract the overall expected log loss over everything. And the reason why we choose this is because actually, if we ignore the O of 1 over n, I think, this chi ends up being equal to the integral of this over all the different x's and y's weighted by their probability. And here's a brief explanation. If we expand the chi of x and y in the integral here, we end up averaging over all the small l's, which ends up turning it into L1 and gets us the delta L, which we wanted.
Yeah, good point about the 1 over n. There's nothing there.
Okay, so now the observable. Yeah, so a question to ask is, what should we use for our phi? Well, let's think. Is there any fundamental quantity in SLT that's easy to compute and highly connected to the structure of our model, which preferably shows up in the free energy equation and which we would like to know its dependence on the dataset used to train our model? I mean, you may have guessed it by the fact that it's up here. The learning coefficient we should look towards. But the learning coefficient is, I mean, we could take the expectation of no, we can't actually take the expectation of the learning coefficient over all the weights. The learning coefficient is a function of a local minimum. But what we can notice is that the learning coefficient is itself an expectation. And we could write the inside of the learning coefficient as phi c. And then we can rearrange some stuff and find that if we just divide the learning coefficient by n beta squared and take its derivative with respect to the dataset perturbation, then that ends up having the same form as a susceptibility. So it's not actually a derivative. I asked Dan about this, and technically you have to do finite differences here or some other fancy thing, but we can pretend it's a derivative for this slide. So we can choose this interior quantity here to be our observable. So let's look at this interior quantity a little bit. In order to implement a weight restriction in our model, we choose some component. We break our model up into a part of the model which is not a member of that component, and a part of the model which is a member of that component. So U and V, where V is a member of the component. We freeze U, and then we only allow V to vary. In terms of expectations, that ends up taking the form of a delta function, so that if you go off of the U path here, all those go to 0, so those don't end up influencing your expectation. So we get the, yeah. So that's how this ends up implementing a weight restriction. That's how technically the local learning coefficient is implementing the weight restriction too. And that's how we can implement a weight restriction inside of our observable. And really, this isn't quite right. Our observables never end up caring about H, I don't think, because we take the derivative at 0. So it's a little bit wrong, but I mean, it's fine. So now we go on to interpretation. So remember, we had the per token susceptibility, and now we have now we know what our phi is going to be. It's a negative covariance between phi c and the difference between the loss on the particular token and the overall loss. So we could take the case where our susceptibility on x, y is greater than 1, in which case if our phi c goes up, then the other part needs to go down. And our phi c is difference between the sampled weight and the actual weight. So we're saying if a small change causes you to do worse, go up, then this means that your loss on the selected data points needs to go down. Said a little bit differently, or inversely. If the small change makes it so that you end up doing better on overall, you end up doing worse on the selected data point. So, oh, that should be a 0, not a 1. So if chi xy is greater than 0, that ends up meaning something like suppression is going on. You'd like change around C, you perturb C, it increases your performance overall, but that leads to a suppression of y in context x. And then same thing when it's less than 0. These can be a little bit confusing. I think that a good thing to do is just mark, okay, chi xy less than 0 means expression, chi xy greater than 0 means suppression. Yeah. So now we get to the exciting stuff. We said we were going to make a big Jacobian matrix, and now we have made the big Jacobian matrix. We have all of our susceptibilities, our per token susceptibilities, on all the different data points, and we have approximately 163,680 data points for each of the different components of the pile that we have. And so those are all our columns. And we have all of our heads as our rows. So we find the susceptibility of each one of these x's and y's with weight restriction 0, 0 or 0, 7 or 0, 1 or so on. And we put that into a big...
Maybe not have just said that these 0, 0 or whatever, these index heads, right?
Yeah, those are heads. So 0, 0 means layer 0, head 0. 1, 0 means layer 1, head 0. And we have 7 heads in each of our layers, and we have two layers in total. So that's where those numbers come from. Now, this is a little
Not that it
bit
really matters, but I think it's 20,000 rather than 163,000, right? We didn't
Oh,
use
that's true. Yeah, we
we didn't use all
downsample in
of the
order to
sample.
actually do the SVD.
Yeah.
Yeah. So now this is technically the transverse of what we promised, but you don't have to care about that. Now we get to results. Well, we do the SVD of this, and then we get to results. And this is the patterns in the data component of the SVD. So we look here. These are our right singular values, right PCs. And we can, each of the right PCs are going to be susceptibilities corresponding to each of the different XY pairs. And each of the different XY pairs can be categorized into a variety of different ways. We chose these really six ways of categorizing them by word parts. That means, is it a inside of a word? Word starts. That means, does it have a space inside of it? Formatting tokens, as you can see, they're like things that nobody would ever say, but computers care about. Induction patterns. I mean, you know what induction pattern is. We had A, B in the past, and the model learns in context that A, B again in the future is probably a pretty good bet. If I see A, then I should probably say B again. And then delimiters. There's two kinds of delimiters, and they seem to have very different expressions in our model. There's open parentheses and closed parentheses. So we have the left delimiters, which are the open, and right delimiters, which are the closed. And we can see each of the different PCs, the PCs go from 1 to 5. Seems pretty specialized in terms of which things it likes. So PC 1, very positive, and remember, positive means suppress. Word parts, PC 2, or it's very negative on word starts. It's very negative on formatting. So you could say it. Oh, what's the opposite of suppress? Express. It expresses word parts. It suppresses word starts, and it suppresses formatting. They could look at PC2 and say similar stuff. It suppresses word parts. It expresses induction heads, and so on. So these are very, very specialized. But you may be saying, do these actually mean anything? Are you just looking at random noise? And the answer is no. And the answer is, how could we tell? And the reason is, the next question is, how could we tell? And the next answer is because when we look at the structure part, when we look at the left singular vectors, we are able to get striking agreement with the developmental with previous Lang 1 work. So uniform mode, in terms of justifying this, not that I mean, it's very interesting, but we could see here we have previous token heads and induction heads active in the second PC, which shows us which things are expressing induction and suppressing word parts, and which things are doing vice versa. So we see all the previously categorized multigram heads. I mean, they're negative, suppress, just invert it. They're expressing word parts, and they're suppressing induction. And then vice versa for the induction circuit. We have our induction heads, and we have our current and previous token heads, and both of those are expressing induction and suppressing word parts. And furthermore, so previously it was found that layer 1 head 6 and layer 1 head 7 both induction heads. But a little bit different in terms of induction heads. It was found that layer 1 head 6 was much more active on, or was much more specialized into code data, while layer 1 head 7 was much more specialized into like language data. This is the difference between shape rotator and word cell. And that, like, I mean, we now have an explanation for why that is. Layer 1 head 6 expresses formatting and delimiters and suppresses word starts and induction. And layer 1 head 7 expresses word starts and induction and suppresses formatting and delimiters. Yeah, I would expect that too if one specialized in code and one specialized in language. Going back to the uniform mode, I didn't put the picture here. If you read the paper or read the paper, uh, you would possibly notice that like uh, different heads are highly correlated in terms of the um, susceptibility on different data points. Um, I mean, that's what we see here. A lot of the variance is made up for by PC1. And like, if we go back and we look at PC1, PC1 is basically expressing word starts, suppressing word parts, and expressing formatting. I mean, it makes sense that like the most basic fundamental thing that all the heads need to know about is the fact that there are words, that spaces separate different words. Uh, I don't know. It just seems like also makes a lot of sense, at least to me. Like spaces represent different words, and there's this other uh, weird formatting nonsense, which you also need to like understand exists. If like that's also probably the first thing that I learned when I was learning about language, at least how to write language. I mean, I guess I knew about letters, but it's I mean, don't maybe I did. I think I probably did know more about word spacing rather than letters. Let's see, do I have anything else to say here? Oh yeah. So we could look at the multigram heads here. Uh, the express word parts. Again, this I think makes a lot of sense. Like a thing that you're going to pick up a lot on by, like, if you're just in charge of memorizing stuff, it's pretty smart to go and memorize like the word continuations. I don't know. That also makes a lot of sense to me. Um, yeah. So this, I don't know. I'm very happy with this work. I feel like it's like really. I don't want to overclaim. I'll overclaim once the video turns off. How about that? Um, yeah, like it's a step in the direction of absolute of solving mechanistic interpretability. I mean, it's very striking that we could just do all of what we did in language one uh, by just completely like it took how long to do language one? It took like once we get the susceptibilities going and we just press do the PCA on our computer, it just like spits out all of this. There's some there's some stuff we're doing where I mean you're not going to be able to inspect each of these PCs by hand, so you could give the corresponding. Uh, this is getting a little bit into overclaiming territory, so I think we could stop here.